Most of the big AI models we hear about all the time, they learn kind of like a student who's just cramming for a test with a giant stack of flashcards. They're shown millions and millions of examples, and every single one has been hand-labeled by a person. But what if an AI could learn about the world the way we do? Not from labels, but just by watching, and by constantly trying to guess what's going to happen next. Well, today, we're going to dive into a really cool AI called PredNet that does exactly that.
All right, so here's the game plan. We're going to start with the big learning problem that holds back a lot of AI. Then, we'll look at this fascinating idea from our own brains that might just be the solution. After that, we'll see how that idea was actually built into an AI, and then, the fun part, we'll put it to the test, first in a made-up world, and then out on the open road.
Okay, let's kick things off with Section 1, the AI learning problem. To really get why an AI like PredNet is such a big deal, you first have to understand the biggest hurdle in AI today, and that's its constant need for a helping hand.
So on one side, you've got what's called supervised learning. This is the powerhouse behind most of the AI we use today. It works, for sure, but man, it takes a ton of human effort. We're talking people manually labeling millions of images. This is a cat, this is a dog, over and over. It's a huge bottleneck. But then on the other side, you have the holy grail, unsupervised learning. This is where an AI learns patterns all by itself, just from raw, unlabeled data, just by observing. This is so much closer to how you and I learn, right? And it totally gets rid of that massive data labeling problem.
And that brings us right to the big question the creators of PredNet were trying to crack. How in the world do you build an AI that can learn useful stuff about the world on its own without spoon-feeding it all the answers? Turns out, the blueprint might have been inside our own heads this whole time.
Which leads us perfectly into Section 2, the brain's prediction engine. Yeah, to solve this huge problem in artificial intelligence, the researchers looked to neuroscience and this really elegant theory about how our own brains figure things out.
The theory is called predictive coding, and the core idea is, well, it's beautiful. It says your brain isn't just a passive sponge soaking up information. Nope, it's an active, non-stop prediction machine. It's always guessing what you're about to see, hear, and feel. And here's the really important part. It learns the most not when it gets things right, but when it gets them wrong. That feeling of surprise, the error between what it predicted and what actually happened, that's the golden ticket for learning. And this is how that amazing feedback loop works. It's so cool. If you look at the diagram, a higher level part of the brain, that R, makes a prediction, which is A. That prediction gets sent down the chain to be compared with the actual sensory input, the A. Now, the difference between those two, that creates an error signal, E. And that error signal, the "whoa, I didn't see that coming" moment, is the only thing that gets sent back up the chain to fix the model. Think about it. Only the surprises travel up. It's just incredibly efficient.
Okay, so you've got this awesome brain-inspired blueprint, but how do you actually build it? How do you turn that theory into code? Well, that's where PredNet comes in.
PredNet's job is really simple, but profound. It's a deep neural network, and its one and only goal is to watch a video and, at every single instant, predict what the very next frame is going to look like. That's it. Nobody tells it, "That's a car," or "That's a person." It has to figure all of that out on its own, just by trying to make its predictions better and better.
And this diagram just brilliantly shows how they translated that brain theory into a neural network. You can see that every layer has its own representation unit that makes a prediction. That prediction is then compared against the target, the actual next frame, and the difference generates an error signal. It's the whole theory right there in silicon. Predictions flow down to be tested, and only the errors, the surprises, flow back up to teach the model what's really going on.
So, the theory is elegant, the architecture is super clever, but does it actually work? Does it learn what we think it's learning? To find out, the first test was in a controlled environment, a synthetic world where the researchers knew all the rules.
So what they did was train PredNet on thousands of short videos of these 3D rendered faces just rotating. And take a look at this. The top row is the real video footage. The bottom row is PredNet's prediction, frame by frame. On that very first frame, the prediction is just a blurry mess, right? It has no clue what to expect. But watch what happens. After seeing just 1 or 2 frames, bam! It locks onto the motion, and its predictions become incredibly sharp. It's figured out the trajectory.
And this gets to the absolute heart of the matter, which is captured perfectly in this quote from the original paper. To make predictions this good, the AI can't just be
I don't know, copying pixels. It has to be building an internal or implicit model of the object itself. It has to have some kind of understanding that this is a solid, 3D thing that moves and rotates in a predictable way.
But, this leads to a pretty fair question. Okay, the predictions look great, but did it really learn anything about faces? Or is it just a super fancy video copying machine? How can we prove that the knowledge it's building is actually useful for something else?
And this is where the proof gets really, really cool. The researchers took that internal understanding that PredNet learned only from predicting rotating videos, and they used it for a completely different task, identifying static pictures of faces. And as you can see from the chart, the knowledge PredNet learned just blew the other models out of the water. It was significantly better than other leading unsupervised models. See, the act of predicting the motion forced it to learn a much deeper, more flexible understanding of what a face actually is.
Okay, so that's pretty impressive for a clean, synthetic world. But the real test for any AI, right? It's the messy, chaotic, totally unpredictable real world. So for the grand finale, they took PredNet out of the lab and put it on the road.
They fed it thousands of hours of dashboard camera footage. And just look at these results, it's amazing. On the top, you've got the real footage. As a car passes by, look at PredNet's prediction underneath. It totally nails the trajectory, and it even fills in the road that gets uncovered behind the car. It anticipates how the shadows are going to move on the pavement. When the car turns a corner, it correctly predicts how the scenery is going to shift into view. It's kind of mind-blowing.
And again, this looks absolutely incredible. But we have to ask that same tough question. Is this just a cool visual trick, or has the AI learned something fundamentally useful about driving a car and navigating the real world?
And the answer is a resounding yes. Check out this graph. That black line? That's the actual steering angle of a human driver in the video. The blue lines are what a simple program was able to estimate the steering angle to be, based only on the internal brain-like activity inside PredNet as it was watching the video. I mean, it's not perfect, but that correlation is just stunning. Simply by learning to predict the next frame, the AI developed an internal representation that implicitly understood the physics and dynamics of the car.
And the numbers here really seal the deal. This chart shows the error in that steering angle prediction. The understanding that PredNet learned on its own was 35% more accurate at this task than a comparable, more standard AI model. This is the ultimate proof. The model isn't just making pretty videos, it is learning a high-quality, genuinely useful model of the world that can be directly applied to real-world tasks.
So, what are the big takeaways here? Well, first, this powerful idea from neuroscience that we learn by correcting our own predictions can be built directly into an AI. Second, by giving an AI a simple goal like predict the next frame, it forces itself to build an internal model of how the world works, its objects, and its rules. And maybe most importantly, this knowledge, learned without any human labels, turns out to be incredibly useful for real, practical applications.
And that just leaves us with this one last fascinating thought. I mean, if an AI can learn the basics of physics and what objects are just by watching videos, what else could we teach it? What kind of amazing intelligence could emerge if we stopped spoon-feeding it answers and just gave it a window to our world and an endless curiosity to just ask, what happens next?